In this example, we are given with a beam that has a load on it, and it is in the form of a triangle, and it is called uniformly varying load with zero magnitude here at A and W at the end or at B. The first step is to find the reactions. So by the way, what we're looking for here is to find the shear and moment diagram of this beam right here loaded with this load. Alright, it's shear and moment diagram and also the shear and moment functions. So to solve for the reactions, let's take moment at B. And so the moment at B, which is equal to 0, is just basically this reaction. So that's going to be, that causes a clockwise rotation about B. So that's going to be RA times L. And let's equate it directly to all the load that could cause counterclockwise. So it's going to be clockwise equals counterclockwise, and so this area is going to be just the area of a triangle. So that is 1/2 of base, which is L, and then the W. Alright, so that's the magnitude, and its distance is L over 3 about B. Alright, so that's what the moment equivalent to our RAL. So if we write that down, that's going to be 1/2 LW times L over 3. So now if we simplify, we can cancel L and L here, and we're left with WL over 6. So the reaction on the left side is just going to be 1/6 of this W times L, the load. That's the first reaction. And for the reaction at B, let's do sum of the moment at A equal to 0. Then again, assume that this reaction is going upwards, as well as upwards. So since at A, then RBL would be our first moment about A, and then this one, it could cause opposite direction of this. So this causes counterclockwise, while this causes clockwise about A, so they are equal. So RBL times, of course, the area 1/2 LW times its moment arm. Since this is L over 3, then the other side must be 2L over 3, or 2/3 of L. So if we simplify this equation here, L and L gets cancelled out, and also this 2 right here, that's are all equal to 1, and we have WL over 3 as our reaction at B. So now we found out what's the reactions, so we can make it smaller and write it here. This is WL over 6, because it's smaller. Its reaction is smaller because it's right here is just smaller compared to this point. So WL over 3 here. Alright, at B. And to make sure if these reactions are equal to the loads because of the equilibrium, then 1/2 LW must be equal to the sum of these two. Right, so let's try and check if it's indeed. So this one, it's just not necessary step, but it's a strategy that you can use, so you can check if your answers for the reactions is correct. Because otherwise, if you don't check it and you messed it up all the way down, it's more time consuming. So it's better late than never. So WL over 6, so this would have 2 times 2, still 1 to have the same denominators. As you can see, 2WL plus WL is going to be 3WL, or WL. There's no 0 here based on our given, so this would become 1/2 WL, which is indeed equal to 1/2 WL. Alright, moving on to what we really want here. We can cut our beam in this manner, wherein our x is greater than or equal to 0 but less than or equal to L. So that's going to be here, or here, That's going to be our x. We want to know what's the function right here. And so if we cut our beam right there, we're gonna have this cut portion. Then if we continue here, this is our original. So if you notice, right, our load is W here, but here it's no longer W. So what we're gonna do is find the height of this by taking this as our basis, this as our x, and this as our entire length. Alright, and this as our new y. Let's say that's y. So since these triangles are similar to each other, you can take advantage of that by saying y is to x, the ratio is equal to w is to l. And so w is to l, and we can say that the height of this is going to be w times the x, how far we are from our starting point here, divided by l. So if we check that, this is our 0 right here. This is our 0, and while this is our point L right here. So if you check at x equals 0, it's indeed our load is equal to 0. Our load here is 0, right? And also if you check at x equals L, right, you substitute L right here, we're gonna have WL over L, which is, it turns out to be our y at this point on our L is indeed W. Alright, so we can replace this y as W x over L. That's the new height. Now our shear positive convention here is this one. While for our moment, it's going to be this one. This direction, counterclockwise, because it causes our beam to sag, while this shear causes a downward, and our beam will go upward, and that's why this is our positive convention. And also, let's not forget our reaction here. We found out that that's WL over 6. Now, to find the shear function, just basically look at your shear. Our shear function would be whatever load that opposes the direction of our function will be positive on the other side. So as you can see, this WL over 6 is opposing the direction of this shear. So we'll put that as positive on the other side. Right? So that is WL over 6. And also, there is another force right here due to this small triangular load with height WX over L. Sorry for this, WX over L. Alright. Now, its magnitude is still the area of this triangle. So that's going to be 1/2 the base times WX over L. So this is the magnitude of this small little triangle here. So as you can see, it is along with the direction of our shear. So what we're going to do there is make it negative. So 1/2 x times WX over L. Again, take this as your point. Whatever the force that would be opposite to the direction of your shear, just like this load, take that as positive on the opposite side. But this is our shear right here. This is opposite, so let's make that positive here. And this is along with our force. They're all downwards, so take that as negative here. And simplifying it, we'll get W. Why am I writing this O right here? It's WL over WL over 6 minus, for this one, it's going to be WX squared over 2L. Alright, and this is now our shear equation. And they said that in order to locate the maximum bending moment present on our beam due to this load, shear must be equal to 0. When shear is 0, moment is max. So we have WL over 6 minus WX squared over 2L. And if we solve for x squared, this W will get cancelled out, right? And transposing this whole term here, we're gonna have x squared over 2L, which equal to L over 6. Since we are just looking for the distance, we're gonna disregard the negative root. So x squared here will have two roots, positive and negative. Diba? And since we're just looking for the distance, there's no negative distance, so it is just acceptable to do like this. So x squared, it will become 2l squared over 6. And then simplifying this would become 1/3 of l squared. Alright, and then x squared. Taking the square root of both sides, we're gonna have the square root of 1/3 l squared. And the square root of l squared is going to be l over the square root of 3. Square root of above over square root of below. And if we rationalize this, this will become square root of 3l over 3. So this is the distance and location of our maximum moment from point A. This is our point A here. So if you like, this is already valid here. If you take the square root of this, like square root of 2 over 6 L squared, you can have it as is. But there's simpler form like this one. Alright, this is the location of our maximum shear. For the moment, let's keep it right here first. Alright, for the moment function is going to be about this point right here of our shear. So just take note, our moment is counterclockwise. So all forces that cause opposite of this, so this is counterclockwise. So all the moment right here, like this one, that could cause clockwise or opposite of this, will be positive on the other side. So W L over 6 is positive and its moment arm is x. So it's x distance away from the cut. So here we cut here. So we take moment at this point. So let's write it down. Its moment arm is x. So W L over 6 times x. That's our first moment. Well, our second, this, of course, that force. And as you can see, it's the centroid of the triangle. The x bar is going to be 1/3 of the base. Our base is here is x, right here. So we're gonna have 1/3 of x, or just simply x over 3. That's the distance. This is the force. So let's write it down as negative. So why negative? Because it's along our moment. This is what we're looking for. So it's along the moment, right? So it will have negative sign on the opposite side. So 1/2 wx squared. Or this is the simplified version, right? Wx squared over 2l. So we can write it wx squared over 2l. So this is just the load times the moment arm, which is x over 3. So x over 3. We simplify a little bit further. We're gonna have L over WLX over 6 minus WX cube over 6L. So as you can see, it's obvious that here we have second degree curve, while here we have third degree because of this. So it's pretty convincing that we haven't yet made errors, right? Our computation from the top is still correct. So this is our moment function. Now if we wanna find the magnitude of the maximum moment present in the beam, right, due to the loads, you'll just have to substitute this value. This is the location to our moment function, and the result will be the maximum. So m at x is equal to square root of 3 over 3l would give us WL over 6 and square root of 3. Am I right? Square root of 3l over 3 minus W 6l square root of 3 over 3l raised to the third power. And simplifying it, we have, for this one, we have square root of 3 WL squared, like this, and this, all over 18. 6 times 3 is 18. While here we have square root of 3 raised to the third power times W, and also L cube. Okay, this one will get cube, and also this one will get cube. Alright, so we have 6L times 3 cube. Right, all of this will get cube. So this one is this one cube, and also this as this one, and this one, and below is this 3 cube and 6L. Alright, As you can see, L will get cancelled below, and this will become L squared. And alright, that's it. Square root of 3 WL squared over 18 minus, so this square root of 3 raised to the third power is going to be what? But before that, let's simplify this below. 3 to the third power is equal to 27. Alright, that's 27. While above, we'll have, and here above, if we look at this square root of 3 raised to the third power, it's going to be square root of 3 times square root of 3 times square root of 3. So this 2 will simplify to 3 and just multiply it by square root of 3. So above, we're gonna have 3 square root of 3 W and then L squared. And below, this 6 times 27 will simplify to 162. Above will remain 3 square root of 3 WL squared. Then here in this term, it's just the same, but then gonna multiply it to something, so we will have the same denominators right here. So it turns out that if we multiply it by 9 over 9, above will become 9 square root of 3 WL squared. This will turn out to be 162. And since they have the same denominators now, we can combine them. So 9 square root of 3 WL squared minus 3 square root of 3 WL squared. Right? So if you have 9 of this amount and 3 of this amount, and you subtract this value to this 9 of that, we're gonna have 6, 9 minus 3, square root of 3 WL squared over 162. And this value right here, you can further simplify it as square root of 3 over 27 WL squared. So this is now the value of our maximum moment. Just plug in any values for your W, assuming that it's a triangular load just like the given. Multiply it by the length squared and times this factor, and you're gonna have maximum moment. Alright, so if we plot what we get here, you're gonna see that this is our shear. Our shear on the first point is WL over 6. Alright, and also at distance x, which is square root of 3 over 3 of the length away, that's going to be our maximum moment, wherein our shear is 0. So as you can see here, the degree. Alright, as you can see, for the load, it is a triangular of first degree, so our drawing must be of second degree on the shear. Well, as you can see, this is the loads are negative and the slope is increasing. Alright, so if we write that down, this is the most useful mnemonics: PD, ND. Please do not neglect neglect dumb people instead. So as you can see, our load here is negative. The loads are negative when it is downward, so we have negative load while its slope is increasing, so our curve will look like this: NI, negative increasing. Alright, so going back to our diagram, from here, this will become like this one. So of course, this will be negative WL over 3, the reaction, while this is second degree. So for the maximum moment, it's just this one moment. It would be, since this is a positive, so this here is positive, while this here is negative, and the slope is decreasing. So this is above and then below, so decreasing. Then we're gonna have positive decreasing. This is PD, NI, ND of PI. So we have here positive decreasing. So we're gonna have this right here, third degree. Alright, this is the maximum, the peak. And then we're gonna have here is negative and also increasing, right, from 0 to this value. So negative increasing. So it will be look like this, third degree, and its value at the top, this one here, the maximum shear for this configuration is square root of 3 over 27 W times L squared. Alright, let's see. That's it. We're done with this problem, and that's it, guys. Thank you so much for watching. Peace out.